In this week's video, we will be talking about hybridization and bonding modes. We will be doing two problems. For the first problem, for the following molecule, determine the hybridization of all 9 hydrogen atoms and count the number of sigma and pi bonds. This is actually the molecule caffeine. So now what we need to do is look at all of our atoms and determine the hybridization. The best thing we can do is start in one specific place and go around through the entire molecule. The best place to start for our hybridization is in the upper right-hand corner. Notice that this carbon is going to have 4 attachments. 4 attachments means 4 hybrid orbitals. This will be an sp3 hybridized carbon. So now let's go to the nitrogen below. Notice that there are 4 attachments, 3 bonds and a lone pair. This is also going to be sp3 hybridized. Our carbon here has only 3 attachments. The double bond only counts as 1 attachment. So now this is going to be the different hybridization of the sp2 hybridization because we only have 3 attachments. Then for our nitrogen, we have a single bond, a double bond, and a lone pair. This is going to be sp2 because of having only 3 attachments. Our first carbon in the ring has only 3 attachments, 2 single bonds and a double bond to the other carbon. This will also be sp2 hybridized. The carbon above it is in the exact same format, so it will also be sp2 hybridized. For our carbon at the top, notice that it has 3 attachments, 1 to a carbon, 1 to a nitrogen, and to the oxygen with a double bond. So that will be sp2 hybridized. For our oxygen, we have a double bond and 2 lone pairs. This would also be sp2 hybridized. For our nitrogen, notice that we have 4 total attachments, 3 single bonds and a lone pair. This will make this sp3 hybridized. For our outer carbon, it has 4 attachments. This means it will be tetrahedral in molecular geometry, making this sp3 hybridization. Our carbon here has 3 attachments, the double bond being 1 attachment. This will be sp2. Our oxygen, having 3 attachments, 2 being lone pairs and a double bond, will also be sp2. Our final nitrogen has 4 attachments, 3 single bonds and a lone pair. This is going to make this sp3 hybridized. And finally, our last carbon has 4 attachments, making this tetrahedral, sp3 hybridized with a bond angle of 109.5 degrees. So now that we've determined the hybridization for all of our non-hydrogen atoms, we must count the number of sigma and pi bonds. The best place to start is the pi bonds. Remember, any multiple bond must be created by a pi bond. So the carbon-nitrogen is 1, our carbon-carbon is 2, our carbon-oxygen is 3, and finally our other carbon-oxygen is 4. There are 4 pi bonds in our molecule of caffeine. If we were to have a triple bond, we would need to count 2 pi bonds for each. So now we must count the sigma bonds. This is easily done by numbering all single bond attachments as well as our multiple bonds because there's a sigma in each one. So we have 1, 2, 3, and 4. We have 5, 6, 7, 8 connecting our carbon and nitrogen, 9 in our double bond, and 10 connecting carbon and nitrogen. We have 11, 12, we have 13, 14, 15, 16, and 17 connect our hydrogens. We have 18 connecting the nitrogen to the carbon, 19 connecting our carbon to oxygen, 20, 21 connecting our nitrogen to carbon, 22, and then finally 23, 24, and 25 connecting our hydrogens. As you can see in this molecule, I have all single bonds counted, as well as also counting part of our multiple bonds, because there is a sigma bond in every multiple bond. This will give us 25 sigma bonds. As you can see with this problem, we handled two very different ideas, the hybridization and then also the bonding mode. Make sure that you are counting all sigma bonds and all pi bonds. For our second problem today, for the following molecule, determine the hybridization of all carbon atoms and determine what orbitals are creating all carbon-carbon connections. So we have our molecule. You will see that not only does it contain carbon, but nitrogen and oxygen, but we're going to focus in on our carbons. The first carbon we want to deal with is located here on the right side of the molecule. Notice that it has 4 attachments, and this will give it sp3 hybridization, and we would expect that carbon to have a tetrahedral molecular geometry. For our next carbon, also has 4 attachments, and we would expect for this to also have the sp3 hybridization. Now you will notice that this carbon has only 3 attachments. This is going to be an sp2 hybridization. The next carbon has only 3 attachments and is sp2 as well. This carbon has 3 attachments, a double bond to a carbon, 1 to the oxygen and 1 back to the other carbon, but it is still sp2. This carbon has the same structure as the last one, so it will be sp2 as well. And finally, you will notice that with our last 2 carbons, they have the same 3 attachment arrangement, giving us the trigonal planar molecular geometry, so they're both sp2. So now we have to look at our bonds and figure out what orbitals are creating all of our connections. Notice that our first carbon-carbon bond is going to differ from our other carbon-carbon single bond. For our first one, we have 2 sp3 hybrid orbitals forming our sigma bond. So how we would answer this is sp3 to sp3, both of them being hybrid orbitals, forming our single bond connection. And that is easily signified by our sigma. For our other carbon-carbon bond, the one connecting to the ring, notice that I have an sp3 connecting with an sp2. So how I would label that is I would say that it's an sp2 hybrid orbital from the ring carbon to my sp3 orbital of the attachment, and this makes a sigma bond as well. So now let's look at the entire ring. Notice that I have all sp2 carbons for the entirety of the ring. So now that means that they're going to have the same hybridization as well as the same binding mode. So for all of my sigma bonds in the ring, they are going to be sp2 hybrid orbitals attaching to sp2 hybrid orbitals of the neighboring atom. So now this gives us all of our sigma bonds. But now the question we have to ask is, what about the pi bonds? Notice that I have 3 pi bonds connecting 6 carbon atoms. So remember, all pi interactions are created by unhybridized orbitals in our atoms. So for all of our pi interactions in the ring, we are going to use unhybridized orbitals from our carbons. If you have 3 attachments, you only hybridize 3 orbitals, leaving 1 unhybridized 2p orbital in each atom. So how we would answer this is the unhybridized 2p orbital of one carbon is going to interact in a pi manner to the unhybridized p orbital of the neighboring atom. So when looking at this problem, remember that all sigma bonds are created by hybridized orbitals, or in most cases, hybridized orbitals. But if you have a pi interaction, whether that's a double bond or a triple bond, you should be able to label that with the unhybridized p orbitals. Good luck.